My name is Paweł Zagórski, and during this video I'd like to show you my project, Aerospace Blockset. This project is developed under Google Summer of Code 2012, and it is a work in progress. This is the state at the end of the week 6, sixth week of coding. My configuration is CLab 5.3 on Fedora desktop with GNOME shell. As you can see, Celes Lab is already installed. Celes Lab is a prerequisite library for an Aerospace Blockset. And as this is a developmental version, I will start with running some unit tests. All blocks of my Blockset are covered by unit tests. Right now, 3 of them are not running because of the known issues. As you can see, tests are passing, so I will proceed to CLab demos. And I will find my Aerospace Blockset. It should be just underneath the Xcos. Whoa, what's happening? CLab is working really slowly when the screen capture is turned on. I will try to present anyway. Okay. So this is a demo demonstrating satellite on orbit scenario in Aerospace Blockset. I will also run Xcos toolbox to give you a quick tour on the Aerospace Blockset. Okay. So in Aerospace Blockset we have several palettes. First of them being environmental palette. This will contain different models. Currently I only have US 76 atmospheric model. There is palette for equations of motion. Right now there is a secular J2 propagator of a satellite on orbit. Guidance navigation control palette, which currently only has a user input block that allows you to enter Keplerian arguments of orbit. Utilities palette that contains some utilities. As you can see, there is a plotting block that allows to plot ground tracks, angle conversion block, and some blocks for coordinating reference frames. And I also, for my own purposes, have a debug palette which has dummy block. This is a block that is for me a skeleton. I start developing each of my block from this one. So for this simulation, let's see the parameters. Those parameters for Aerospace Blockset are designed in a way that integration time is counted in days. This is a very common thing to do in aerospace. And as you can see, we have 0.2 days, which is about 5 hours of simulation time. And then when I proceed to clock, you will find that clock period is such that this is just below 2 minutes. And this time step makes sense in this particular simulation when we have satellite on orbit. And I will start describing those blocks from Keplerian input block. When you open its properties, you can see that the main purpose of this block is for the user to be able to manually input orbit parameters in Keplerian reference frame. And this serves as an initial value for orbit propagation block. This is a secular J2 propagation, so it takes the initial orbit, and then as time passes, it propagates it and outputs new Keplerian coordinates. But as you probably can imagine, you would like to have those coordinates in Cartesian frame to plot them, to use them. So this is what this MUX is doing. The multiplexer is feeding a coordinate conversion block, coordinate frame conversion block that converts from Keplerian orbit to Cartesian parameters. As you can see, there are two outputs. Those are two three-dimensional vectors. First of them being position in Cartesian frame, and second of them being velocity of a satellite. But so far, at this point, we only have Cartesian position of a satellite and velocity of a satellite, and we are not taking into account the fact that Earth is actually spinning while the satellite is passing over it. So this is exactly what this reference frame transformation does. This converts from G50 vice frame to terrestrial frame, which is tied to Earth's surface. For that, we need to pass a time. This is a time in Julian date, so this is counted in days since the beginning of year 1950. Later on, I would like to develop some blocks that will allow for easier input, but right now I'm just using default Xcos blocks to do that. And at the output of this block, I get again position and velocity. Both of those values are then fed to workspace, and position is fed to plot ground track block, and this block is a configurable way to plot a ground track. So plot the position of a satellite on top of a Earth map. So let's just run the simulation and see what happens. So you can see map of Earth, and you also see a red line which represents satellite, and you can easily see as it moves over different areas. Of course, this is not a real-time simulation. This doesn't represent the real time, and as you will see in a minute, the satellite trajectory is moving farther and farther to the west, and this is because Earth actually spins while satellite orbits it. And next things I'd like to implement are events and visibility, so that the user will be able to calculate when his ground station will have a visual contact or can have a radio contact with a satellite, and some more coordinate frames conversion, some more time handling blocks. Thank you.